Всем добрый день. Меня зовут Oleinikov Roman.
Good afternoon, everyone. My name is Oleinikov Roman. Today I will explain visual representations of harmony. Harmony is a complex, intuitive concept. Can we represent harmony in a visual, geometric form? We will use the natural science approach. What is the difference between the natural science approach and those that are often used in music? There are a lot of textbooks on harmony and on elementary music theory. How do they work when studying musical phenomena? Music may be deconstructed into musical forms, for example, chords, intervals, modes, tonality, and so on. Musical structures are smaller objects, but they still refer to music. Based on a scientific approach, we attempt to reduce phenomena into their simplest form. We reduce them to study their simple form, and then we integrate it back to the whole. What are musical structures based on? They are based on sound. Sound is real, material, that is studied in physics. And sound is involved in music. Music without sound is impossible. We need to study the nature of sound. What determines sound? Sound is determined by the laws of physics, as well as practically everything in this world. And it would be strange if the laws of physics determined everything and did not concern music in any way. So physics determines sound, musical structures are formed by sounds, and musical phenomena are formed by musical structures. What will this approach give us in the future? Firstly, we can present harmonic phenomena such as chords, tonalities, modes, more clearly, more conveniently, more compactly. We can see them. Secondly, we will outline some future prospects. Any good scientific theory has a predictive function. You may know that the planet Pluto was discovered. She was first predicted and only then found with a telescope. A good theory should give us a predictive effect. So let's try to build this scientific theory of harmony. What do we need to do? Imagine that we now have no music, no musical theory. We're in a primitive communal system and decided to create music. So how can we build a musical system? We need to choose some sounds from which we will play, understand how they interact with each other. First we need to choose sound. We will call it a fundamental tone. It is just a starting point. It is a foundation. We know how sound is arranged. Take, for example, the vibrations of a string. When the string vibrates, it produces sound, which pitch is denoted by the letter Nu. Here it is indicated. The pitch is inversely proportional to the length of the string. The longer the string, the lower it sounds. All string musicians know that if you take a string of smaller length, it will sound higher. The volume depends on the amplitude. Volume is not so important to us in this case. I think that all musicians in the textbooks of harmony saw this picture. It is in the first chapters. It is called the physical nature of sound. It, as a rule, is represented and then it is forgotten until the end of the book. What is depicted in it? Harmonics are depicted. A string, when oscillating, does not oscillate only as a whole. It oscillates at once in all ways that are represented here. Suppose that when it oscillates as a whole, it produces a frequency of sound equal to 1. When it oscillates like two half waves, we seem to have two half strings oscillating. The length of the string was reduced 2 times, and the two half strings oscillate. Since the length was halved, the frequency increased twofold. Then the string bends like 3 half waves, like 4, 5, 6, 7, and to infinity, as predicted by the physical theory. All multiple harmonics will be present in the oscillations. If an entire number of half waves are placed on the string can produce such oscillations. How does this happen physically? Here we show how the first two harmonics form. The first harmonic oscillates like this in its entirety, and on it half waves of the second harmonic oscillate in antiphase. This happens simultaneously. As soon as we strike the string, it immediately oscillates in all these possible ways. There is not one sound, but a whole set of sounds. This set of sounds is presented here. There is a fundamental frequency that is obtained when the string oscillates as a whole, and all other sounds that are called overtones. They are multiples. That is, in addition to the frequency of the fundamental tone, there will be sounds that are 2 times higher, 3 times higher, 4, 5, 6, 7 times higher, etc. This structure of sound is characteristic of all string instruments. Physical theory predicts that wind instruments have exactly the same structure of sound. I emphasize this because this is the grain from which we will grow harmony. This is the basis. So we understand how sound is arranged. How can we connect two sounds together so that they have as much in common as possible? There are several ways to do this. Here they are presented. First we'll look here. Below is the fundamental tone with which we started. We have the main sound and multiple harmonics in all integers, 2, 3, 4, 5. If we take the second sound twice as high as the first, that is, it will have a fundamental tone exactly 2 times higher. Harmonics of this sound will be equal to 2 multiplied by 2 to the power of 4, 2 multiplied by 3 to the power of 6, 2 multiplied by 4 to the power of 8, 10, etc. All even numbers. We see that with such a structure, when we take a fundamental tone and a sound that is twice as high, these sounds have every second harmonic in common. These two sounds have very, very much in common. They will be very consonant with each other. They took place practically from the same harmonics. Such an interval of two sounds is used in music. It's called an octave. There is another way to connect two sounds. We take the most fundamental tone and sound, which is 3 times higher. There we look twice. Here we take 3 times higher. We see that every third harmonic will coincide with them. These two sounds will also have a lot in common. Such an interval is also present in the music system. Moreover, music systems are arranged from such an interval. It is called duodecim or quinta through the octave. And finally, the last possibility to connect two sounds that are used in classical harmony is multiplication by 5. The second sound is 5 times higher than the fundamental one. Why don't we take that sound that is 4 times higher? They will have every fourth harmonic in common. Why do we not take it to the base? Because multiplication by 4 we can get from here. We can multiply once by 2, then multiply again by 2. That is, 4 is obtained as a double applied octave. Our base interval is an octave, and multiplication 4 is a derivative. Therefore, we do not need to take it as a base interval. Thus, we have only 3 base intervals. Let's take a 3-dimensional space. These intervals are some steps. We can take the sound, multiply it by 2, get a new sound, multiply it by another 3, get one more sound. That is, we can both multiply and receive more and more sounds. Let's take a 3-dimensional space. There are 3 axes, and we will postpone the steps of multiplication by 2. Here in the center is our fundamental sound, with which we started. If we multiply by 2, we get here. Multiply by 2 more, we get here. Now we will postpone the multiplication by 3 on this axis, and on this axis we will postpone the multiplication by 5. It will be the sounds closest to the fundamental tone. This sound will coincide with the fundamental every second harmony. It has every third, and this one has every fifth. We can receive more and more new sounds from the fundamental tone by such steps. What happens if we move, say, from the fundamental tone to the sound that will be here, per duodecim above, multiplied by 3? What sounds will be closest to it? To it will be the closest sounds that come in one step from it. That's in this direction. This or this.
вот таким способом устроено,
This is what is called the space of multiplicities.
называется пространство кратностей. В англоязычном
In English language literature, the term lattice is sometimes found in German language, tonits.
Немецкоязычный тонец.
On this axis, we put the multiplication by 2, for this multiplication by 3, for this by 5. Multiplication by 2 gives us an octave, and therefore, for us, this axis will not be the most interesting. All notes located in the octave are called identically. In some musical sense, they are almost identical. We will be interested in this plane. I remind that here we set multiplication by 3, and here the multiplication by 5. Multiplication by 5 is a third through 2 octaves. If we paint this plane in those traditional notes that are in the music system, then it will look like this. In the center, say, the note C, the fundamental tone that we have chosen. There will be steps by quints, there will be steps by thirds. This is a third down, in this direction will be a fifth down. That's how these sounds are located. This space shows us how close each other sound are in the space of harmony. The closer, the smaller distance between the sounds, the more they will be consonant, harmonious with each other, because we need to take very few steps. In one quint step, every third harmonic coincides, and if we make 2 steps, every 9th harmonic will coincide, less coincidence. In this space, we see how harmoniously close to each other the notes are. Are these facts documented in music literature? Yes. Yuri Kolopov has in his course of harmony such a table where the intervals are presented in terms of Q and T, quints and thirds, Q and T. For example, the interval C to D is a plus of 2 quints in Kolopov's terminology. And in the space of multiplicities, we make 2 quint steps. Multiplying by 3 is like a quint step. Or, for example, the interval C to E flat, here it is designated as a D sharp, is plus 1 quint and minus 1 third. In this way, we will simply visualize what is there in the form of a column. We can see the geometry in this picture. It becomes clear to us how this works. On this space of multiplicities, one can consider musical phenomena that relate to harmony. It is logical. And the first phenomenon that we will consider is the major and minor. What gives us the major and minor triads? They prepare us for the tonic, they make the centralization of sound. How can we provide this? Centralization can be provided by a crosshair. That sound that falls into the crosshairs is in the middle between the others. Such a crosshair is used to form a major and minor. When we take the major, we take the 2 upper branches of the crosshairs. When we take the minor, we take the 2 lower branches of the crosshair. Both of these structures centralize the sound. And these are the 2 nearest sounds to the selected one on 2 different axes. We take 2 different axes so that the crosshairs turned out and not just some line. Here, 2-dimensionality is important. If we had only 1 dimension, we could not have built a tonal crosshair. This forms the major and minor. Next we move to the tonality area. How do we build a tonality? We have such a crosshair, such corner. It allows us to centralize a note. Now, if we want to add something, we can do the following. First, repeat these corners several times so that the listener is accustomed to the fact that this is not an accidental structure. This corner is important for us. Second, we would like to repeat them symmetrically so as not to lose centralization. And third, we would like to repeat them as close as possible to the chosen note so that the system does not creep in different directions. This was done exactly in this way, by hearing. We get the tonality where this central corner becomes tonic, performs a tonic function. The other 2 symmetrically to the right and left of the elements are the subdominant and dominant. Here the structure of the tonality becomes absolutely clear.
Мы просто можем посмотреть и от любой
We,
ноты построить.
drawing 3 such corners from any note, get a tonality built from this sound.
Получим тональность, вот, построенную от этого звука.
With the minor, all is identical, only the corners will be directed not in this direction but in the opposite direction.
Что же касается
Now, regarding the predictive function,
хотел сказать, и,
it's
наконец,
time to implement it.
ее реализовать. Когда
When we took the corners, we took either 2 axes directed upwards or 2 axes directed downwards. But we have 2 more possibilities to make such a corner.
Сделать такой уголок. Когда мы, ну вот, в математике обычно...
In mathematics, a plane is usually divided into 4 quarters. Then the major is the corner of the first quarter, because we are directed there. The minor is the corner of the third quarter. And we still have the corners of the second and fourth quarters, which in their centralizing structure are arranged exactly as major and minor. They also centralize the sound simply in a somewhat unusual way. We can use them. From these corners we can also build some tonal structure. We can duplicate these corners. For example, we can duplicate a corner of the second quarter on the left and on the right. We will get a subdominant and a dominant. I'll take them in quotes. This is not a traditional subdominant and dominant, but they are built on the same principle. Let's show a system that will also centralize some tone in an unusual way. This is a tonal construction from the second quarter chord. Composer Ivan Soshinsky, who will have the next report, composed a music called Étude, and now we will listen to it. It's 1.5 minutes long. It will show us the tonality of the second quarter. It sounds like this. Here is such a small composition which illustrates the tonality of the second quarter for us. It used not only, of course, the basic functions, even side chords. What did we get as a result? First, we have obtained a space of multiplicities. In this space, harmony appears for us visually. In it, it makes sense to consider all the harmonic phenomena, because there they look much more logical than in any other system. It derives from pure physics. We did not take any other circumstances. We took the physics of sound. From it we got how these sounds interact with each other. Second, we examined the objective nature of musical phenomena. For example, consonants. The closer notes are to each other, the more consonant, more harmonious they sound. They have more matching harmonics. In addition to consonants, tonality, the main functions. On this space, of course, you can consider other phenomena, modes, side chords, etc. I emphasize that we have considered objective nature here. We did not consider the perceiving subject. We have not yet considered questions of perception. They are very complex and still require detailed research. So far, we have taken only objective nature into account. And finally, we laid the foundation for the construction of harmony in new musical systems, for example, microtonal music. Thanks to such a structure, we will be able to build a logic that will work in microtonal systems when we leave the 12-tone scale, and then we will use quarter tone or some smaller divisions. We can build some harmony in them,
Мы еще...
and we will hear about it today.
У меня все.
Thank you for your attention.